Action!
Hello class, this is our project and we will be presenting Sam, Brennan, Ben, and I. For our project, we chose this function here, FAB of x comma y equals the absolute value of a of x plus b of absolute value of b of y. And to examine this function, we will have a value set for a and b, with a being 4 and b being 3.
Damn right.
And that plugged into our function, we can examine the graph of it and see the properties and behavior.
So here we have our function graph. It's not perfectly symmetrical because a and b are not equal. Here we have from the y direction. As you can see, it's not quite as big as it's going to be from the x direction because we're only going out 3 instead of 4. And then from the x direction, it's slightly wider because we're going out to 4. And here's from the top view, so you can clearly see that on the y-axis it goes out to 4, and on the x it only goes out to 3. So now we're going to explore how the models of the function change as the parameters change, so as we move a and b. So as you can see, like when a equals 1 and b equals 3, we have a much wider function, especially in the x direction. Now, as we change like a equals 3 and b equals 1, which is flipping it, it's much longer in the y direction. So then as a and b are both 5, the z value is increasing faster, so it's like this more skinny, more narrow, like higher sloped on each one of the sides for the shape. And then it's the same thing for the negative because we have those absolute values, which is interesting. So, which is also why it never goes below 0, but the function does not change if it's like positive 5a and negative 5a. It'll just be the same. So, like as a and b are each positive 5, like their shape's identical as when a and b are both negative 5.
Alright, so here we have a contour map of the different level curves for our function. And as you can see, each level curve represents a different z value. So z equals 0, z equals 1, z equals 2, etc. And so that z value is equal to the rest of our function. And as you can see, it traces with the shape that Ben already established, right? Like the lower values, 0 and this darker color, are towards the center. And you see it get evenly steeper, and these levels are coming out, so this is a higher value for z as you get to this yellow, this 18. All right, we can go to the next graph. Now, to investigate it a little further, we're going to take a vertical cross-section, and we're going to look at how our function intersects with different planes, right? So we've got one parallel to different axes, and this one isn't parallel to any axes. First, we've got x equals 1. So when you plug that in, you end up with f of x equals 4 plus the absolute value of 3y, and that's going to equal z. And as you can see, we get this nice absolute value pattern. This slope is a little bit tighter. It's not 1. It's going up faster than that. It's going up at 3 and negative 3 because of the absolute value. And because it doesn't intersect with the origin, because of this additional 4, we don't see it reach 0 here, because that's the only time our function is at 0 is when it's at the origin. We can go on to the next one. This red graph has a very similar behavior when we set y equal to 2, so we end up with f of x equals absolute value of 4x plus 6. We see the same type of thing where we get this slope now 4 and negative 4. It's an absolute value, so we have the v, and again, it doesn't intersect the origin, so we never hit 0. We can go on to the next one. This here is when we intersect with the plane of y equals x. So this is on a diagonal. It's not parallel to any of the axes, and we end up with f of x equals 7x equals z, or absolute value of 7x. And we get this same v, but because there's no constant here, it's just 7x, we are intersecting the origin, which means we are going to hit that 0 value down here.
So when looking at the periodicity of our function, f of a, b, of x comma y equals the absolute value of a of x plus the absolute value of b of y, we can determine if there's any repeating patterns by looking at the symmetry of the graph. So, as we can see, starting from the origin, if we look towards quadrant 1, there's this triangle here. We look towards quadrant 2, there's also the same triangle, quadrant 3, same triangle, and obviously quadrant 4, same triangle. And so, it's safe to conclude that graphically, there is symmetry within our graph, or at least some sort of symmetry, right? But we want to look at this not only graphically, but also mathematically. So if you scroll down a little bit, a little higher, more. There we go, stop. All right, so taking our earlier example, when we had the A value equal 4 and the B value equal 3, we can analyze our graph of f43 of f of x comma y equals 4x, absolute value of 4x plus absolute value of 3y. But before we get there, we have to look at just our standard example. And as shown in that graph, we saw that each quadrant was equal to each other. And so any quadrant, any graph that follows symmetry within each quadrant will follow this rule here. What's shown is any x comma y value of a symmetrical graph for each quadrant will also be symmetrical for each quadrant. So this represents quadrant 1, quadrant 2, quadrant 3, quadrant 4. And therefore, with this, we know that this whole portion is equal to z. And therefore, any z value that is fixed, and only fixed, the function will hold for this equality. So, we know that there's some sort of repeating pattern within our graph. And to be able to analyze this further, we could see if the graph follows the rules of periodicity. We see this in a sine or cosine function, where the graph will continuously repeat itself over and over and over. And so any sine or cosine function has to follow this rule. All this says is, if we have some value, x and y, on a sine or cosine graph, and we add some value p, or in this case, some value p to x, or some value q to y, the graph will remain with the same output, right? And so, assuming p and q are greater than 0, if it holds true, the graph will continuously repeat. And so if we scroll down a little bit, we can see if this holds true for our example. So in the case of our function, we know that this is not true. And to prove it, we can simply solve for the vertices. So after solving for what z is equal to, and solving for the x value when y is equal to 0 and x is equal to 0, we can determine what the values are. So we solve and we determine that there's a proportionality, that the vertices of the function is equal to plus or minus z over a, or plus or minus z over b. And we use this knowledge to determine, okay, if z is any fixed value, that the graph will grow, that the function will grow linearly and proportionally to the other one, as both include z. So we know that since this is a linear growth, it doesn't follow the rules of periodicity. And therefore, it will not follow the same rules as a sine or cosine function. So, to conclude, there is a pattern present in our function. The shape will remain as the function grows, as there's a constant linear relationship with z, as you can see here. Therefore, we know that the function has scalable symmetry, which means the graph is symmetrical within its planes, mathematically and graphically. And therefore, this shows that it's not periodic, so it does not follow the rules of periodicity, and actually directly goes against it. Thank you.
Now finally, we're just going to simply look at whether the graph of f of xy equals a to x plus b to the y is both radially symmetric and symmetric under reflections. We're going to look at this in a general sense and a mathematical sense, so we can look at graphs not using the a and b values that we used to parameterize from earlier. And so when we start off by looking at it, as Logan previously mentioned, yes, the graph is symmetric under reflections, and this is because of the absolute value sign in the nature of the functions. And so when you look at f of, when you reflect over the y-axis, you use f of negative x, y, and then you can look all the way through and you see that that absolute value sign removes kind of the negative effect, producing the same value of it equaling f of x, y. You can do this over the x-axis as well, with negative y, produces the same result. They all equal each other essentially, even over both negative x and negative y. And so now, as we understand it is now symmetric under reflections, we can look at it from the perspective of whether or not it's radially symmetric. And essentially what that means is that the distance, as it's written up here, I'll make it more plain. So in the situation where r equals x squared plus y squared, the distance formula we are asserting that essentially that f of x, y is equal to h of r, so that our distance is equal to our output. That would be it being radially symmetric. So, if we look at it from the perspective of not what we parameterize, but from f of 0, f(0,1) and f of 1, 0, this one would equal A, this one would equal B, and in this situation, if we're looking at it from the distance formula perspective, 1 squared for both equals 1. A does not equal 1, especially in our situation with our value of 4,3, and B also does not equal 1. So that means that it is not radially symmetric, and it is because, can you scroll down? Oh, I got it. It's because the value of the function is dependent on A and B as opposed to being dependent on X and Y. So when we look at our contour maps, especially when we change it, as we change the values of A and B, it still maintains its symmetric under being symmetric under the reflections. You can kind of cut it in half. Same thing looking in the mirror, cut it in half. Same thing looking in the mirror, but it is not radially symmetric as values out here stretch further than values out here as you kind of rotate it in that sense. Thank you.
3, 2, 1.
Thanks for
for
watching.
watching.